day, everyone, and a warm welcome to all of you this afternoon on this webinar of ours. We trust that you're going to enjoy it and learn something to take home from here. A special welcome to our attendees. Without you, it wouldn't have helped if we broadcasted this at all. So a warm welcome to you. Then to Pulse Solutions, thank you very much for making this possible and for hosting this event for us. We really appreciate it. And then to our panelists, I quickly like our panelists to introduce himself to you before I give over to them. I am Louan. I'm from Pendo Energy Solutions. I will moderate the session for you. Over to you, Petrus.
Thank you, Louan. My name is Petrus Keswa. I'm a design engineer at Petrus Energy Solutions. I've been here in the electrical infrastructure space for over now like 8 years or so. And then, yeah, that's basically my background. I've done several projects around electrification and so on. And then, Sam, I'll hand over to you.
Thank you very much, Petrus. My name is Sam Mohlala. I'm also a design engineer for Pendo Energy Solutions. I've been in the electrification field for 4.5 years now. So I've worked with a lot of electrification projects, and we are delighted to actually share our expertise and experience with you guys. I'll hand over back to you, Louan.
Great, thank you very much, Sam, and thank you, Petrus. And I can assure our attendees you're in good hands today. Just a little bit of background. Our whole course that we're running is electrification or principles, of this, distribution design networks. And our previous session was just an overview in general. And today our topic will cover overhead line design. And then still to come in our next two sessions will be specifically underground design networks, and then also a hybrid, which is a mix between the two. So for today, our concentration is on overhead line designs. So without any further ado, I'm going to hand over to Petrus Keswa. He's going to start with the presentation, and then he will hand over to Sam, and then directly after that, we'll start with the questions and answers. I hope you enjoy it.
Okay, as Louan has indicated, today's session is on the fundamentals of electrification design. The whole presentation today's structure will just cover like the design aspects, how we go about when we are appointed to do designs on behalf of our clients, either being supply authorities or private developers. The whole focus for today will be on overhead residential electrification design. And then I'll also just provide like a brief recap of the previous session of what we actually presented. And all of that, as we indicated on our previous session, we basically have 3 phases in the design process. The first phase being inception, as well as concept and viability. From there, the design development phase with procurement and documentation. And then as well, the final phase, which is the contract administration as well as closeout. That's where the actual infrastructure gets installed on site by a contractor. And then as we've previously indicated, all of these are based with the assumption that the funding as well as the land availability agreements have been concluded. Then on the next step, as I've indicated, with the overhead electrification network design, I'll just provide like brief applications where these designs are carried out. So the overhead networks are predominantly carried out on informal settlements. This is due because in most cases with informal settlements, the layouts and the town planning has not been formalized yet. So that's part of the reason why our overhead electrification is implemented in informal settlements. And then it's also predominantly applied on the lower LSM. LSM is your living standard measure, the lower level LSM housing. And then in some instances, we also find it so in what we call the middle to high old suburbs in some metropolitan areas, as well as some smaller towns. It's also predominantly applied as well in peri-urban areas. This is predominantly due to distances in there, like in peri-urban areas, it's plots, like dwellings are not close to each other. So the load density there, it's really low. So that's why we also use overhead electrification. And then as well, obviously in rural areas. And then the part of my interest as well, I actually did a postgrad with electrification network design topology. And then my research topic there was to try to find a model to get to decide how you get to apply these network topologies. Essentially, how do you decide on which network topology you can use for a particular neighborhood or a development. So, but ultimately the decider, like the major person which has an influence there is the network operator or the supply authority. Because at the end of the day, the network in most instances belongs to the supply authority. In some private instances, it will belong to like the network operator, which might be a private individual or a private entity. So the moral of the story is that like the whole decision around which network topology to use is a subjective decision, it's not an objective decision. And then part of the primary factors which influence that, firstly, obviously, the technical requirement has to be met, design level has to be met. So that is the primary factor. And then from there, like the other factors which also influence that decision, it's around the financial aspect of which is the cost of the project. As well, this is not just like only the capital cost of the project. We also need to also look at the life cycle cost of the project as well. And then we also go into the issue of reliability, as well as the aesthetics around the network as well. And then I'll also just touch over on the benefits of overhead electrification network. The first point there is with regard to reliability. With an overhead network, faults are easily identifiable because all the infrastructure, it's visible to you, it's visible to see with the naked eye. And as well from there, like the duration of the interruptions, it's much shorter. And then in terms of maintenance, it's easier to maintain. In terms of the capital cost, the initial capital cost of overhead network, they are much less compared with an underground network. And with conductors, like overhead conductors, have a higher current carrying capacity when you compare them with a similar cable of the same cross-sectional area. Then with overhead conductors, because they are overhead, like there is no insulation. Well, the insulation medium around it, it's air, so you can easily overload them. And as well as I've mentioned in terms of the life cycle cost, obviously when you decide, you have to check in terms of like between like the different topologies, which one will cost you not only just with the initial capital cost, but we also have to look at the entire life cycle of the network. Okay, in terms of the shortcomings of the overhead network, and then the overhead network is essentially prone to environmental conditions. In terms of lightning, it's exposed to external lightning. As well as if you have obviously like a thunderstorm or so, like an overhead network will be prone to that. As well, if we have windy conditions, you might end up with conductors clashing in some rare instances. Fortunately for us in the country, we're not really prone to snow, but there are some areas in the country which are prone to snow. Maybe I can just give to Louan there just to give his experiences where he encountered a few instances in the country where we had issues with snow. Louan?
Great, thank you very much, Petrus. Yeah, I used to be work as a clerk of works in the Eastern Cape and did a few projects for Eskom in that area. And it was in the, I don't know if everybody know where Berkeley East is, but that is when you travel on the N6 straight down to from Bloemfontein to East London, and you go over into the Eastern Cape, you get Allable North, then you go towards Lesotho side, and that's where you get Berkeley East and Rhodes, where Tiffendale Ski Resort is. And I actually one year during all those snowstorms and stuff met the Eskom operators there who actually showed me photos of where the line that went uphill to one of the cell phone towers up on the mountain was so packed with snow that it actually hanged 1.5 meters from the ground. So they actually had to isolate that line and waited a few days for the snow to melt off the line before they could energize it. So it was actually heavily packed with snow and caused additional sag on the line. So there's definitely areas in South Africa where it happens, although it's very, very limited.
Okay, thanks, Louan. Okay, and then also another shortcoming of the overhead network is obviously with the aesthetics. Some people see it as not being easy on the eye. Then in terms of reliability with overhead networks, the frequency, you actually end up with the frequency of the faults is more often there, as well as the service interruption. But the duration can actually be for a shorter duration, but the frequency of how often it occurs, it's actually more on with overhead networks. Then there's also an issue with the perceived public safety because with overhead networks, you can see the infrastructure. So some people perceive that as being a bit safer than like with underground networks, but it's just it's just a perception. And then Sam will also go into detail, touch on the regulatory requirement in terms of the clearances for the different conductors, either being insulated or uninsulated conductors. And then with this actually happens in most cases in urban areas where you have overhead networks. In there, like there has to be continuous cutting of trees close to the conductors to ensure that like the faults on the network is reduced, because you don't want trees being closer to the conductors, because like you'll end up with service interruptions. Then in some instances, it is a bit prone to illegal connections. Some people perceive it as with overhead networks, people can easily do illegal connections on overhead networks. In terms of our experiences as well, like in the country, we actually don't have proper systems in place where like proper records are kept on the frequency of interruptions as well as the durations of interruptions per network topology. We are aware that obviously NERSA does require the licensed distributors to keep records of interruptions as well as the duration of the interruptions, but that is actually only kept for the entire distribution network of a particular network operator. So like it will actually be more beneficial though if we also had to keep a record of these interruptions per network topology. That will actually essentially also help us as well, not from the design side as well as from the operational side, to make the decision easier on deciding which network topology to essentially use. Then on this slide, I'm not going into a whole lot of detail, because on the previous webinar, we actually touched on essentially the deliverables as well as the requirements of the phase one of the design process. That's where we essentially get to determine the load requirements as well as the supply authority standards. And then we also get to know if there's any existing infrastructure. And then we also get to go into the development layout as well. And then now I'll just hand over to Sam to go into the detail of the next phase of the design process. Sam, I'll stop sharing on my side, and then I'll hand over to you to start sharing from the phase 2 of the development, design development process.
Now that we know that we have this particular development that we have to electrify, and it has been decided that we're going to use overhead network or topology. We know how many customers we have to electrify, so you have now calculated your load. You know how much load requirement is required for the development. So I'm just going to take you now through the steps of designing for an overhead network, starting with the MV. So these are the things that one should consider when designing an overhead network. For MV, you have to take into account conductors and equipment sizing. For overhead, it's predominantly bare conductors, with the exception of few cases where you find insulated MV conductors. You have to now decide which type of cable or conductor that you're going to use and the size that you're going to use. So whether it could be Ming or Hank conductor, you have to decide now so that you can create your MV ring or backbone. Another thing that we have to look at is your pole types and lengths. So different supply authorities prefer different types of poles. Other municipalities, they prefer to use concrete, others wooden poles. So you'll have to liaise with your supply authority and understand which preference of poles do they prefer to use, and then you use that. Overhead pole transformers, you have to now decide the size of the transformer that you're going to use, and also liaise with your supply authority on which type or sizes that they prefer to use. Other municipalities, they have a fixed standard of pole transformers that they prefer to use. It's easier for them in terms of maintenance and replacement of transformers, so they have it available on stock. MV structures and configurations. This you also have to be guided by your supply authority. We have horizontal, flat, delta, and staggered. So this can be used one or two of them, but supply authorities normally have a certain preferred configuration that they want to use for overhead networks. So you'll have to liaise with them and ensure that you're actually designing according to their standards and they're happy with that. MV pole structures, we have intermediate poles, which are just 0 degrees, there's no deviation there. And then strain poles, these are the poles that can have anything above 5-degree deviations. Terminal poles, these are your end poles. Stays and struts, these are supporting structures that keep your poles in place and prevent them from leaning or tipping over. Protection requirement. On your network, we use links, fuse sectionalizers, and auto reclosers. So the primary purpose of these protective equipment is to ensure that they protect your network and electrical equipment from electrical faults. So they ensure that our electrical equipment are not subjected to high-level faults that exceed the rating of the manufacturer's equipment. So they actually make sure that the electrical equipments are not stressed beyond their limits. Earthing and bonding, which is also a very important aspect. The primary purpose of actually earthing is to ensure that your electrical equipment and living beings are actually protected from electrical shocks by actually discharging the electrical energy into the air. So there's few actually things that you can do in terms of earthing for your poles and transformer equipment. Normally on transformer equipment, what they do, you can earth your MV and LV together. However, that can only be done if your overall resistance to earth is below 1 ohm. But normally the normal practice would be to actually earth your MV and your LV separately from each other. On clearances, you have roads and other services, so you have to consider the length of poles that you have to use when you cross, and roads and other, and also take into account other services that might be on that road or desired route that you're taking. And then shared structures, this refers to structures that might be used for MV and also for LV. So mostly poles we use them for MV, and then that very same pole can also be used for LV as well. And then I'm moving on to clearances. Clearances table. This shows you the clearances for uninsulated overhead conductors. As you see from the left, we have your minimum safety clearance, ground outside township, ground inside township, railway lines and proclaimed roads, roads in rural areas, roads with entry or exit, communal land, private property, buildings and structures, communication lines supported on the same structure, and other power lines. So you see there's different voltages and minimum clearances that are required. So this is a very useful table that one can actually use when designing. This is just a typical MV layout showing you, this is a project actually from Riting project, a project that I was also involved in. So as you will see, you have a blue line coming from the substation. I'm not sure if you can see my mouse there. This is from the substation, and then this is a ring going all around like that, and then back to the substation. And then on the ring, you also have few spares. So this is your first spare, and this one is second one, and things like that. So, but your main backbone, it has to be decided, and then you have to actually optimize and take the best route. As you can see, as Petrus have mentioned, overhead, we normally use it on informal settlement and also low house costing. So this was an informal settlement. So the roads were actually tricky. So you have to actually go to site and inspect and then decide on which route to use, and also taking into account cost as well. And then on the LV design, still you have to also consider conductor sizing. On the LV side, we predominantly have insulated conductors, and there is some cases where you find the conductors are not insulated. So you have to also calculate which conductor size that you're going to use, and on how many customers are you going to put on that feeder, and then decide on that. Equipment sizing, we have pole top boxes. Different municipalities prefer different pole top boxes. Others, they use protective pole top structures. Others, they just prefer a normal fiberglass box. So it could be 2-way, 4-way, or 6-way. So you have to, depending on the supply authority standards and requirements, ensure that you use that particular protective pole top box. Miniature circuit breakers. These are the breakers that you have to put on the protective structures, so they protect your customer service cables. So on the miniature circuit breakers, you have to also take into account the type of curves that you're going to use for the breaker. So using your discrimination for the system, normally the circuit breaker that we put on the pole top box, it's your orange toggle, which in terms of curves, it will be curve 1. So curve 1 means this breaker will trip second or last before the breaker inside your customer unit. Pole types and lengths, you also have to take into consideration the length and also the type of poles that are going to be used. So obviously now if the wooden poles or concrete poles were used on MV, it will be the similar type of concrete used on the LV as well, since it will be under the same supply authority. LV pole structures, even on the LV as well, we do have intermediate, strain, terminal, and stays and struts. So these are the same. Intermediate, it's It has no deviation, it's zero strain. It has an angle or deviation about 5 degrees. Terminal, it's your end post, stays and struts, they just provide support to your LV pole structures. Protection requirements, fuses, we normally use fuses to protect your feeders. So also you have to calculate the type of or the size of fuses that you have to use for each feeder. Earthing and bonding requirements. This also now depends on the supply authority, but most supply authority prefer to use the TNCS method, whereby your supply is earthed, your supply thing live is it's earth at your supply, and your earth and neutral is combined. Yes, and then on clearances, you also have to take into account clearances as well. So for LV, the clearances, you can also use that table. But since it's insulated, the minimum clearance is actually neglectable according to NRS. Street lighting, on street lighting, we can use the same LV structure or a separate poles and overhead conductors. But that will depend on whether your design, you have separate street lighting or the street lighting is within that very same electrification area. And then depending on that, you can add an additional cord to supply purely the street light away from your main LV infrastructure. But if it's combined, you can use your ABC with 5 core, which includes that street lighting within that ABC conductor. And then also decide on the luminaires that you want to use, internal roads, the wattage that you're going to use, taking into consideration the space in between, and also the height of your poles and the angle of projection of your luminaires. Shed structures, on LV, we also have shed structures. So we can utilize some of the MV or structures that were designed for MV for LV purposes as well. On service connections, you also have to take into account the conductor sizing. So this will depend on what ADMD was decided upon and how much amps are you giving the customer or the end user. On pole types and lengths, that will be the same topology that will be used depending on the supply authority. Whether it's concrete or pole or wooden poles, it will be the same throughout from MV, LV, and service connections. Now these normally called kicker poles. These are your customer poles, so they're installed normally inside the stand yard to actually service each dwelling or unit. Service connection pole structures, we have terminal poles normally. Protection requirements, there is the customer must have a DB or a ready board, which also has miniature circuit breakers. As I've mentioned before, on your pole top box, you have a CAV1 breaker, and then on your customer unit, you will have a CAV2. So the CAV2 will trip first in conditions of a fault, and then on the pole top box, if the fault is not cleared on the first breaker, then it will trip at the top pole top box. Clearances, you have to just take into account the clearances when servicing those units and ensure that they are high enough not to for children or other material or obstacles in the way that can actually damage your service cables or conductor in this case. Metering, depending on the municipality as well. Other municipalities, they use split metering. Others, they just use smart meters or just direct metering. So that will depend actually on the municipality as well, or the supply authority. And then the clearances also have to be taken into account. And this is just a table that shows you the clearances of insulated conductors. As you can see, you have on your, from my left table, column 1, you have your nature of surface or activity underneath the line or rated voltage. And then on 2, there's your LV ABC cables. And then on number 3, you have your concentric or service cable. So these are the clearances that, or the tables that you can use to actually guide you in deciding or meeting the minimum requirement of clearances. And then this is a typical drawing for LV and service connections. This is also a meriting project. I'll just go to another slide where I'll just take you through some of the stuff. As you will see here, this is your transformer zone marked in orange line. So we call that a transformer zone. Transformer zone is feeding a group of customers. From your transformer, you have feeders going out and servicing individual customers. So there's few symbols or colors that you see here. I'm just going to take you through that. The square and a circle symbol that represent your MV and LV shared structure. So this tells you that this pole is actually shared between the MV and LV. And then if you look at your pink circle, that indicates that this is your intermediate pole. And then the orange circle, it's a circle with a half orange in it. This tells you this is a strain pole. And then this pole at the end there with sort of a triangle or squarish thing in it, that's a terminal pole. So you have all those symbols representing different types of poles. And then the black and white poles, these are your kicker poles. These are the poles that you use to service each stand. So as you can see, there's a service connection going to each unit. So even if in this stand or unit, there's a lot of dwellings in there, the electrification is a connection per stand. So you don't, let's say, for example, there were 2 or 3 dwellings within that stand, you're gonna electrify all of them. So it's only one connection per stand, and not connection per dwelling. So this is just a typical drawing showing you how the overhead electrification will look like. And then there's also numbers there. If you can see, there's 227, 224. These are your voltages. So after designing your network, we have to simulate it using Retic or other related software that can perform the same task to see your volt drop limits, if they are acceptable or not. And then this shows you that the volt drops were within limits, and then we were happy with the network. And then you can modify it if your volt drop limits are not met. And then I'm just going to touch now on the construction and inspection. This is actually just a recap of what we presented the last time. So each and every project must go through all these phases. So after your design and simulation and you're happy with your design and your supply authority has approved everything, and then now the next stage is to go through construction administration, quality and financial control, factory acceptance testing. That's where now your project is under construction and you do a factory test acceptance of the equipment, commissioning and testing. When the equipment are now transported to site and installed, they have to be tested again to ensure that there's no potential damages while transporting. And then before energizing the equipment, we have to be 100% sure that they are satisfactory according to the standards that they were designed at. And then after that, as-built drawings will be generated, and then a closeout report will be prepared that will be submitted to the supply authority as well. These are now site pictures. As you see on the picture, you have a transformer, and then above it, you have your overhead conductor, that's your MV. And then the black conductor, that's your ABC. And then you have pole protective structures or pole boxes. And then your street lighting as well is also on the same structures there. But there will be cases where you do street lighting separately and then you use separate poles and conductor as well. And then this is another picture. This shows you that we're doing transformer testing or polarity test, insulation, etc. So these were tests that were done before energizing the mini support, the transformer itself. So these are the tests that will be done, and then the supply authority will come to site and witness those tests. This is a picture showing you service connections from your pole top box into individual units or dwellings. And then this is your kicker pole over here, servicing the other customers behind the front customers. And that's the end of the presentation, and I'll hand over back to Louan.
Great, thank you very much, Sam and Petrus, for a very insightful overview on overhead line designs. I see we have about 10-15 minutes. We already received 4 questions, which we'll start answering now. So the first question that we have received, the question is, what process is involved in producing and manufacturing these conductors? What opportunities and finances is available to enter this market? So first of all, I would just quickly, I'm going to answer that question. And the process to actually manufacture these cables, it all starts with a continuously hot rolling AA 1350 aluminium bar, or then a similar aluminium alloy to form a rod. What they then do is they heat it up to 300 to 400, between 300 and 400 degrees Celsius, and they turn the rod and they pull the rod into a wire, which then gets stranded to form a cable for an overhead conductor. Now, the reason why they mainly use aluminium is because aluminium is a metal which is a good compromise between conductivity for electricity, and also the mechanical strength of it. And also then they look at the weight. It shouldn't be too heavy to reduce the sag, and also cost factor. Please note, aluminium is not the only material that they use. It's just the most common material that they use. I know the question is more into how do you enter this market to maybe become a manufacturer, but unfortunately, we all are consultants and we're not really involved in the manufacturing or cannot really assist with that. There's a few big manufacturers in South Africa, like for instance, Aberdeen. They're one of the manufacturers. So we unfortunately cannot assist on how to enter the market. We merely specify the products to be used that is available on the market for us to be used. So I hope that answers that question. The second question, and I would like Sam to answer this question for us. The question is, what support and opportunities are available for SMMEs in this industry? Sam, can you elaborate a bit on that question for us?
Thank you, Louan. On projects that we were involved in, normally the developer will, appoint a contractor, and the main contractor with relevant experience will actually take over the job. And then on that area, it's an obligation sort of for the main contractor to use SMMEs or the local SMMEs around that area that we're electrifying. So there is opportunities in terms of appointing those SMMEs. So they use SMMEs and then they gain experience and grow when we do those projects. And then that will give them future opportunities to actually tender on their own and actually handle a sort of medium and hopefully now bigger project or mega project.
Great, thank you very much, Sam. And then the third question that we have, and Petrus, I'm going to ask you to elaborate a bit more on that. This is a technical question. They ask, does medium voltage line experience volt drop, and why? So is there also a volt drop on medium voltage lines, and why is it so? Thank you, Petrus.
Okay. Thanks, Louan. Yes, like volt drop across the board, like even on medium voltage, you can experience voltage drops, but predominantly in the, let's say in the metro areas, because of like the areas, it's not the load density, it's higher in within metropolitan areas, so we don't really necessarily experience volt drops on the on your medium voltage network. But it is possible if you go to say like on rural areas where you have longer lines and so you will be. But like on medium voltage, the volt drop it's negligible. It's not as high as say on your LV networks. Just to add on that as well, the main issue, it goes back to the fundamentals as well. It's basically the application of the Ohm's law. So because with loads essentially modeled as constant currents, so the only variable that you have on your system is your voltage. That's why there is then a volt drop. I presume that I've answered that question, Louan.
Yes, thank you very much, Petrus. So if your resistance is then fixed and your voltage go up, obviously your current goes down, and then lower currents will obviously have a lower voltage drop on the network. So that's exactly why they actually elevate voltages as well, to have then lower currents, to transfer more electricity from one point to another. And then that also assists with volt drop. So yeah, no, thanks for answering that question. We've got the fourth question that we received is, what is the future for meter readers as a company in South Africa? So this is a very nice question, because I mean, more and more meters gets installed as being prepaid meters, which don't actually get read by a meter reader. We're moving into 4IR, where everything gets automated, so meters get modems connected to it to send data straight through. So meter readers, actual meter readers, is less and less involved into the process. So it's definitely a fact. It won't happen overnight. There's quite still a few meters to still be read in South Africa. It is a costly exercise to replace the meters, but it is definitely going to happen in the next few years, that conventional meters will be phased out completely. I still believe that meter readers will have a role to play, maybe not to directly read the meters, but then also to go and inspect meters, because there might be faults or errors being sent from the meters which need to actually be inspected. So there'll definitely be a role to do that. And to perform tests on meters to ensure that they perform correctly. And then even if all this information comes directly through on a platform, there's always the background that need to be managed, and to make sure that the process runs smoothly, and that all the rates and stuff is actually applied correctly to all the meter readings and stuff come in. But yeah, definitely something to think about. And I believe meter readers, the companies themselves, need to reposition themselves more into electronic environment to see where they can actually still play a role in the meter process. We've got a question here that says, when placing the poles, how do we determine the distance of the poles in terms of MV and LV? Sam, do you maybe want to take this question to say, how do you determine the distance between the poles for MV and LV networks?
I'll pass it to Petrus. He wanted to actually answer the question.
Okay, great. Thank you, Petrus.
Yes.
Okay, no, it's fine. I'll give it back to you afterwards, Sam, to add on. No, the main constraint with the pole spacing, it goes back to the clearances. You have to, on your LV, let's say on your MV, there's a minimum clearance that you have to maintain. So, like obviously with the sec and tension, so during the summer times, like it's predominantly hot. And then like you'll have more sec on your conductor. So during that time, that clearance that on the presentation that Sam indicated, you still have to be within that clearance. So if your clearance, you're not within that clearance, and then you'll have to put the poles closer together or like increase the pole spacing. I'm not sure Sam wants to add more onto that as well.
I think that's fine, Petrus. The only thing that I can just add is you just have to, for LV, if you go 30 meters apart and more, then you're gonna have issues of sagging. On the MV side, you can actually go longer. I mean, I think about 50 or so meters apart, it's still fine. So those are the guidelines that I can add on.
Yes, perfectly. Thank you, Samuel. And it all depends on which size conductor you use. So you'll have to have a look at the characteristics of that specific conductor that you use, the weight of it, the sag. It's all have to do with sag, because Sam have also shared a table with minimum clearances. So we need to stick according to law to minimum clearances from ground to different voltages of conductor, and then also between the different voltages of the conductors, we need to have certain clearances. So it's all got to do with clearances and sag, and yeah, and then the temperatures outside, as Petrus have mentioned, definitely plays a huge role. So it might differ from area to area. I think that actually concludes our session. Please be on the lookout for our next session coming up, and advert will be circulated. Be on the lookout for it in the next weeks to come. Our next session will then cover specifically underground electrification design networks. One more comment that just came in. They said, thank you for the informative session. Petrus answered my SMME question nicely. Thank you. I'm coming from a land development background, working in the industry, energy infrastructure space, with the application of GIS to optimize network designs. What are the development in the GIS application so far? Is there anybody that would like to comment on that?
I'll just touch a bit there. I think it's actually Sam who answered the SME questions. I'm not taking your...
Yeah, that's it.
Yeah, in terms of GIS, like obviously when we do our designs, we obviously use CAD. So like with our CAD software, there's a link between that as well as the GIS as well. So like, but in our space, we obviously get that information from the surveyors and then we just do our designs based on the layout that they provide to us. Hopefully,
Yes.
I've answered the question.
It's perfect. And if I can comment a bit on that, because I've worked a lot in rural areas, especially when there's mountainous areas, and all of that information, the different heights and differences, you can't always see that good on Google Earth, for instance. And in those areas, what we normally do with line designs, there we send a surveyor out to actually do a on-site design or a preliminary design. So they'll literally walk the site and with the GIS technology, basically do the design as they are on site, and then import it into a drawing where we then do the final detailed design stages. So it's definitely being used for a few years already, and very important, specifically when you go into rural areas where you can't see height differences that easier. But if you're on a flat surface, obviously it's not that difficult to do it on paper. Great, everybody. Thank you for joining into our session. Have a great afternoon, and we're looking forward to see you in the next session. Thank you all.